Swayam Prabha. Digital India. Educated India.
Welcome you all to the lecture number 8 on the topic diesel cycle in module number 2 in the subject thermodynamics and thermal engineering. Before deriving the thermal efficiency, having a look at the PV diagram and TS diagram, a numerical question on this topic, let us have a small recap on what we have discussed in the previous lecture, that is lecture number 7. Lecture number 7 we have started with the comparison between the air standard cycle, which is the ideal cycle, and the actual cycle. So there are primarily 4 to 5 assumptions have been made. First one is in the ideal cycle or the air standard cycle, the working fluid behaves like a ideal gas. So air is considered as the working fluid throughout the cycle, and it is a closed cycle. The specific heat of the working fluid remains constant, it does not vary. The conventional combustion process in the actual cycle is replaced by a constant volume heat addition process in case of Otto cycle, and the exhaust process is replaced by a constant volume heat rejection process. And one more difference is all the process of the air standard cycle are internally reversible. So this Otto cycle it is the ideal cycle on which a petrol engine works. However, there are deviations between the actual and the ideal cycle. If you want to implement this ideal cycle in the real practice, there are practical difficulties, because if you see the constant heat addition process which takes place at constant volume, that is, the heat addition process takes place at the end of compression stroke, just before the beginning of the expansion stroke, that is the power stroke. So for the volume to remain constant, that means the combustion has to take place so rapidly. So which is possible only in an ideal case, it is not possible in the actual case. So that is one challenge which is faced. And similarly, the heat rejection process, if you see, it is considered to take place or to happen at constant volume heat rejection, that is process 421. So whereas in the actual cycle, the exhaust gases are discharged to the atmosphere through the exhaust valve, where the piston moves from BDC to TDC. So there is a significant change in the volume. So doing that process in real time practice at constant volume is not possible. So with this background, let us get into the contents of the diesel cycle. First, I will explain the PV diagram, the pressure volume diagram, and the temperature entropy diagram. What are all the various processes involved? Then the very important one, the derivation of the thermal efficiency or the air standard efficiency of the diesel cycle, and one numerical question, so that we can understand the theory and the practical application of this cycle better. So this is the PV diagram and TS diagram. Like the previous lecture, as I explain the process one by one, I will simultaneously draw the diagram so that the students can have better clarity. So like Otto cycle, the diesel cycle also 4 processes. It comprises of 4 processes. So first, on the left side, I am going to plot the PV diagram. Y-axis is pressure, x-axis is volume. This is the TS diagram, temperature and entropy. If you compare Otto cycle and diesel cycle, the process 1 to 2, it remains the same. Isentropic compression. You can see process 1 to 2 is isentropic compression of the working fluid. The working fluid is the air. Air is considered as the working fluid throughout the cycle in all the processes. So isentropic, let me draw the TS diagram first. Isentropic compression, where the compression begins at state point 1 and it ends at state point 2. So this is the temperature before compression, and this is the temperature after compression process. So entropy is constant. if you see the x-axis value, entropy is equal to constant, reversible adiabatic process. So, the same process is represented by like this 1 to 2, okay, 1 to 2, where the volume decreases from V1 to V2, pressure increases from P1 to P2, P1 to P2. So, this is isentropic representation of isentropic process on a TS diagram. This is the representation of an isentropic compression process on a pressure volume diagram. There is a change in the heat addition process, that is process 2 to 3, when we compare Otto cycle and diesel cycle. In case of Otto cycle, the heat is added at constant volume, the process takes place at constant volume. In case of diesel cycle, it takes place at constant pressure. Because of this reason, the diesel cycle is also called as constant pressure cycle. Like how the Otto cycle is called as constant volume cycle, diesel cycle is referred to as constant pressure cycle. So, since the pressure is constant, the line will be perpendicular to y axis. This is process 2 to 3, constant pressure. This is almost a similar line, pressure is equal to constant, heat is supplied. I am using the same notation Qs and Qr. Qs is the amount of heat supplied during heat addition process, Qr is the amount of heat rejected during the heat rejection process. Okay. So, now this is constant pressure heat addition, Qs, constant pressure heat addition. When we say heat is added at constant pressure during the process 2 to 3, P2 will be equal to P3, pressure at state point 2 will be equal to pressure at state point 3. So, I am writing here P3 is equal to P2, P3 equal to P2. So, this is state point 3 on a TS diagram. So, process 2 to 3, this is the difference, constant pressure heat addition. This is the only difference between Otto cycle and diesel cycle. So, you can see here 1 to 2, 2 to 3. Next 3 to 4 is as usual the commencement of power stroke or the expansion process, isentropic expansion, that is 3 to 4. So, this will be similar to 1 to 2, okay. Isentropic expansion, that is the power stroke, and 4 to 1 is like Otto cycle. In diesel cycle also the heat rejection takes place at constant volume only, there is no change in that one. So, 4 to 1 is heat is rejected at constant volume, not at constant pressure. And here in the PV diagram, volume is x-axis. So, the line will be perpendicular to x-axis. So, this is heat rejection, So, in a diesel cycle, Qs takes place at constant pressure and heat rejection takes place at constant volume, If you see the properties which remain constant on the PV diagram, if you see pressure at 2 is equal to pressure at 3. So, this is constant, P2 is equal to P3 and V1 is equal to V4. This is because 2 to 3 is constant pressure, here pressure is equal to constant 2 to 3 and during the process 4 to 1 volume is equal to constant. So, because of this reason P2 equal to P3 and V1 is equal to V4, and of course, the entropy at 3 will be equal to entropy at 4, Similar to Otto cycle, the peak temperature which is obtained during the diesel cycle is at state point number 3, This is the maximum temperature This is the maximum temperature. The maximum pressure also is attained at 3. However, that pressure is equal to the pressure at state point 2. So, this is P max. So, let me rewrite it again neatly. So, this is maximum P max is equal to P3, which is equal to P2. This is very, very important. P max is equal to P3 is equal to P2. In case of Otto cycle, the maximum pressure is attained at state point 3. Here it is 3 as well as 2, because pressure at 3 is equal to pressure at 2. And the lowest temperature will be at T1, the lowest pressure will be at P1. The next highest would be state point 4 in case of pressure. Temperature it will be 4 based on this diagram. Then the highest temperature and temperature is attained at state point 3. Okay, so this is the maximum temperature, and the pressure is at P3 and P2, both are same. So, the major difference between the Otto cycle and the diesel cycle is the heat is added at constant pressure. So, when we say heat is added at constant pressure, the equation that will be used is Cp into delta T. It is not Cv, it is Cp into delta T. Similarly, heat rejection process, there is no change, that will be Cv into delta T. So, process 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 is constant volume heat rejection, like exactly similar to Otto cycle. Now, with this background, let us derive the thermal efficiency of a diesel cycle, which the derivation is little bit lengthier when compared to the Otto cycle. Otto cycle derivation is very easier. We expressed the temperature T3 in terms of T2 and T4 in terms of T1. So, the temperature terms easily got cancelled, and we got the air standard efficiency or the thermal efficiency of the Otto cycle as 1 minus 1 by R power gamma minus 1. Gamma is equal to 1.4 for air, that is the ratio of Cp and Cv, and R is the compression ratio, which is nothing but V1 by V2. Like Otto cycle, I will be doing the stepwise derivation. So, though the derivation is I have provided in the PPT, so that it is easy for the students to understand. So, it is a quite lengthier one compared to the efficiency of the Otto cycle, but still we will do it. So, let me draw the PV diagram again. This is 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So, this is QS, this is QR. One important thing is, any thermodynamic cycle, the marking of arrow marks is very, very essential. Suppose if I have a thermodynamic cycle in which the process direction, a single process or all the processes direction are not marked, then the diagram become meaningless. It does not make any sense. As I said before, all the power cycles, the arrow marks would be in the clockwise direction. You take the Rankine cycle, which is the basic principle which is employed in steam power plant, or which is also called as thermal power plant. The arrow mark on the TS diagram or the pressure volume diagram, the arrow mark would be in the clockwise direction. You take the Otto cycle, diesel cycle, the next one is the dual cycle. All the power cycles will have the arrow marks in the clockwise direction. If you see the process, analyze the process 1 to 2, 2 to 3, 3 to 4 and 4 to 1, the direction in which the arrow just moves, as we mentioned various processes, it will be in the clockwise direction. Cycle like refrigeration cycle, the vapor compression cycle, that has an arrow mark in the anti-clockwise direction. So, by looking at the direction in which the arrow is pointing or pointed, one can say whether it is a power cycle or a refrigeration cycle. So, this is PV diagram. P2 is equal to P3, Okay. And let us have the TS diagram. One to 2, 2 to 3. This is pressure equal to constant, this is volume is equal to constant, this is heat rejection 4 to 1. This is 1 to 2 is compression, 3 to 4 is expansion, and this is heat addition, Okay. So, heat addition takes place at 2 to 3 and heat rejection takes place at 4 to 1. So, let me define the efficiency. Efficiency is equal to output by input. Output is the net work produced during the cycle. So, W net divided by heat input is the heat supplied. I will be using the same notation as I said before. What is the net work done by the engine during the cycle? It is the amount of difference between the heat supplied and the heat rejected. Heat supplied and heat rejected. This is what we have seen in the Kelvin-Planck statement of the second law of thermodynamics. So, this is Qs. So, we can simplify Qs by Qs is 1 divided by Qr by Qs. So, this will be equation number 1. Okay. Now, we will substitute the value of Qs and Qr. Qs is supplied at constant pressure. So, that is what I have mentioned here. Qs is supplied at constant pressure and Qr is at constant volume. So, accordingly I will write the equation. Q is equal to, assuming 1 kg of working fluid. So, Cp into delta T, the process during which heat is added is 2 to 3. So, if you see the temperature, this is T3, this is T3, this is T2, this is T2, this is T2. So, delta T is T3 minus T2, T3 minus T2. So, this is 2. Similarly, write the equation for heat rejected. Heat rejected is equal to constant volume. Heat is rejected at constant volume. So, Cv into delta T. Heat rejection is from during this process 4 to 1. So, higher temperature is T4, lower temperature is T1. So, Cv into T4 minus T1. This is similar to Otto cycle. Substitute 2 and 3 in 1, 2 and 3 in equation number 1, 2 and 3 in equation number 1. Thermal efficiency of the cycle is 1 minus Qr is Cv into T4 minus T1 divided by Cp into T3 minus T2. We know the ratio of Cp to Cv, that is gamma. So, here I have got Cv by Cp. So, Cv by Cp is the reciprocal of gamma. Okay. So, let me write the step by step. We know that gamma is equal to Cp by Cv. Therefore, 1 by gamma is equal to Cv by Cp. So, I am going to substitute 1 by gamma for this term. 1 by gamma for this term. So, the efficiency will be reduced to 1 minus, that will be 1 by gamma. So, 1 minus T4 minus T1 into gamma of T3 minus T2. So, this is the thermal efficiency of the cycle in terms of all the 4 temperatures T1, T2, T3, T4 and gamma. Now, I will be expressing the temperatures in terms of the compression ratio, gamma, etc. So, then we will substitute the values and I will keep T1 as it is, T2 will be expressed in terms of T1 and gamma, etc. T2 also will be, T3 also will be expressed in terms of T1 and T4 also will be expressed in terms of T1. In we can alternatively we can do like this also. T2 we can express all the temperatures in terms of T2 or temperatures in terms of T3 and T4, anything we can follow, but the final answer will be the same. Okay. So, this is equation number 4. I will be using this equation number 4 at the later stage, So, let us see this one. So, 1 minus T4 minus T1 divided by gamma into T2. Okay. Now, I am going to define compression ratio like the previous one. R is the compression ratio, that is R V1 by V2. This is the this one. So, this is V1. Okay, this is V1. Let me extend this line. So, this is V1, this is V2. So, this ratio V1 by V2 is the compression ratio, and there is one more ratio that is called cutoff ratio, that is R suffix C. R is the compression ratio, RC is the cutoff ratio. Okay. So, the heat addition begins at state point 2 and it ends at state point 3. So, what happens in the actual diesel engine, that is the compression ignition engine, which is the other name for diesel engine. First, the air is compressed alone. Unlike petrol engine, in petrol engine both air fuel mixture is compressed, but in case of diesel engine, compression ignition engine, only the air is admitted into the air fuel, only the air is admitted during the suction stroke, and at the end of the first stroke, that is after the suction stroke, only the air is compressed. Whereas in case of a petrol engine or spark ignition engine, during the second stroke the compression is done by the piston on both the air as well as the petrol. At the end of the compression stroke, the ignition takes place and combustion. In case of a diesel engine, the air which is compressed to high pressure and high temperature, at the end of the compression stroke, the diesel is atomized by a fuel injector. We do not use a spark plug, we use a fuel injector. So, which sprays the diesel, and the ignition takes place, followed by the ignition and the combustion takes place. So, the air fuel mixture is not compressed in case of a compression ignition engine, only the air is compressed. And the next 3 strokes of the diesel engine are similar: power stroke and the exhaust stroke, where the exhaust gases are sent out to the atmosphere through the exhaust valve. So, now here cutoff ratio, so ignition, the spraying this ignition and the combustion process is this one. Of course, the combustion process replaced by heat addition process. So, this is the point at which cutoff starts and cutoff ends here. So, cutoff ratio is V3 by V2, volume at 3 divided by volume at 2. So, this is the volume at 3, So, in addition to compression ratio, which is V1 by V2, which is denoted by the letter R, here one more ratio is introduced, that is cutoff ratio, that is V3 by V2, which I will be using later in the derivation. Now, consider the process 1 to 2. One to 2 is isentropic compression. So, write the relation between temperature and volume. T2 by T1 is equal to V1 by V2 whole power gamma minus 1. The same relation which I have used for the numerical question as well as for the previous derivation, Otto cycle derivation. We know that V1 by V2 is R. So, this is equal to R power gamma minus 1. So, using this formula we can write T2 in terms of T1, T2 in terms of T1 into R power gamma minus 1. So, if you look at this equation, now I am keeping T1 as it is, T1 is kept as it is, this is kept as it is, T1 is kept as it is. I will be expressing T2 in terms of T1, T3 in terms of T1, T4 in terms of T1. So, the T1 terms will get cancelled and we will get the mathematical expression. So, now I have expressed T2 in terms of T1, T2 in terms of T1. So, this will be equation number 5, equation number 5. So, here if you see T2 in terms of T1 and compression ratio R and the gamma value. So, this will be equation number 4, okay, 5. This will be equation number 5. So, this is what I have mentioned here, T2 equal to T1 into R power. Of course, here it is equation number 6, slide. I have used equation number 1 is the efficiency, the first equation. So, it does not matter. So, next I am going to consider the process 2 to 3, consider the process 2 to 3. Okay. Process 2 to 3. The property which remains constant during the process 2 to 3 is pressure, P2 equal to P3, constant pressure heat addition process. Okay. So, the pressure is constant, pressure is constant. So, apply the basic equation P2 V2 equal to MR T2. I have taken M as 1 kg. So, R into T2, P3 V3 is equal to R into T3. Divide the first equation by second equation, or you can do the vice versa also. Okay, R term will get cancelled. P2 is equal to P3 because 2 to 3 is a constant pressure process. Therefore, these terms also will get cancelled. Therefore, we will get V2 by V3 equal to T2 by T3, or in other words, T3 by T2 is equal to V3 by V2. If you recall what we have defined V3 by V2, V3 by V2 is nothing but cut-off ratio, it is nothing but cut-off ratio. So, I am going to replace V3 by V2 as R suffix C. So, R suffix C. So, from this T3 is equal to T2 into R suffix C. So, I have expressed T3 in terms of T2, but my aim is to express in this derivation all the temperatures in terms of T1. I have expressed T2 in terms of T1. Now, I have expressed T3 in terms of T2. Since T2 is expressed in terms of T1, I will be using equation number 5 and here. So, replace this T2, substitute the value of T2 using equation number 5, So, this will be T3 is equal to T1 into R power gamma minus 1 into RC. So, this will be equation number 6. So, by using equation number 5, okay, let me write using equation number 5. Using equation number 5, I am replacing this T2 in terms of T1 and R power gamma minus 1. Now, the temperature T3 is expressed in terms of T1, compression ratio R, gamma, and cutoff ratio RC, that is V3 by V2. Okay. So, this is what I have, see T3 equal to RC into T1 into R power gamma minus 1. So, this will be equation number 7. So, as per our equation number, it will be 6. So, I have expressed T2 in terms of T1, T3 in terms of T1. The only temperature which is left yet to be expressed in terms of T1 is T4. Okay. So, for that I am going to consider the process 3 to 4, process 3 to 4. Process 3 to 4. What is process 3 to 4? 3 to 4 is isentropic expansion. So, I can write an expression similar to process 1 to 2, process 1 to 2. Okay. So, T3 by T4, if it is T3 volume will be V4, if it is T4 volume will be V3 whole power gamma minus 1. Look at the pressure volume diagram, V4 is nothing but V1, V4 is nothing but V1 because 4 to 1 is constant volume heat rejection process. So, that I am going to substitute. So, but V4 is equal to V1, therefore, T3 by T4 is equal to, instead of V4 I will write V1, V3 will be equal to V3 only because 2 to 3 is constant pressure, only the pressure at 2 is equal to pressure at 3, volume is at 2 is not equal to volume at 3, which we can easily infer from the PV diagram. Volume at 2 and volume at 3 are different, they both are not same. they both are not same. So, whole power gamma minus 1. To simplify further, multiply the right hand side of the term which is inside the bracket by V2, multiply and divide by V2, multiply and divide by V2. So, T3 by T4 is equal to V1 by V3. I am multiplying by V2 and dividing by V2, so that the term on the right side does not change, So, multiplying and dividing by V2. Take this term, this V1 and this V2. This V1 by V2 is nothing but compression ratio, R, and V2 by V3 is the reciprocal of cutoff ratio. So, that is 1 by RC, 1 by RC. So, this becomes R by RC whole power gamma minus 1, that is T3 by T4. From this I am going, therefore, T4 is equal to, so let me write in the next slide, T4 is equal to T3 divided by this ratio. Therefore, T4 is equal to T3 divided by R by RC whole power gamma minus 1. So, you can see here T3 by T4 is equal to R by RC whole power gamma minus 1. From this I have found the value of T4, that is T3 divided by R by RC whole power gamma minus 1. My aim is to express all the temperatures of T1. Already I have expressed T2 and T3 in terms of T1. Now T4 is in terms of T3. T4 is in terms of T3. But in equation number 6, I have expressed T3 in terms of T1. Now I am going to use equation number 6 here. So, using equation number 6, replace T3 in terms of T1, therefore, T4 is equal to, let us see what is equation number 6, T1 into R power gamma minus 1. Let me bring this RC before the bracket. Okay. So, T1 into RC into R power gamma minus 1. This is using equation 6, the numerator, divided by R by RC power gamma minus 1. So, this can be written as T1 into RC into R power gamma minus 1 divided by R power gamma minus 1 divided by RC power gamma minus 1. This term and this term will get cancelled, and this RC power gamma minus 1 will go to the numerator. So, T1 into RC power gamma minus 1. Again we can simplify further this, T1 into RC, this can be written as RC power gamma into RC power minus 1, okay, RC power minus 1, yes. RC power minus 1 can be written as 1 by RC. So, this is equal to 1 T1 into RC power gamma into 1 by RC. RC and RC will get cancelled. So, finally, we will get T4 is equal to T1 into RC power gamma. So, this is equation number 7, So, have a look at the equation number 5, T2 is expressed in terms of T1. Equation number 6, T3 is expressed in terms of T1, of course, compression ratio and other terms are also there. And in equation number 7, T4 is expressed in terms of T1 and cutoff ratio and gamma. So, keeping T1 as it is, I have expressed T2, T3 and T4 in terms of T1 and other terms like gamma, R or RC. Okay. Now, I am going to substitute 5, 6, 7 in equation number 4. 5, 6, 7, the values of T2, T3 and T4 in terms of T1 from equation number 5, 6, 7 into equation number 4. Substitute 4, 5, 6 in 7. So, the thermal efficiency is equal to, let us see the equation number 4, okay. 1 minus T4, let me see here itself, 1 minus T4 minus T1. So, instead of T4 I will substitute equation number 7, 1 minus, what is T4? T4 is T1 into RC power gamma, this is T4, minus T1 I will keep as it is. So, this is the numerator, T4 minus T1 divided by T3 minus T2, there is already one gamma here, So, gamma into T3. What is T3? T3 I will take from equation number 6, T1 into RC into R power gamma minus 1, this is T3, and T2 is from equation number 5, T1 into R power gamma minus 1, T1 into R power gamma minus 1. Okay, so, this is what I have explained. T4 is T1 into RC power gamma minus T1 divided by gamma term is there into RC into T3 is expressed in terms of T1 compression ratio and cutoff ratio, and T2 is expressed in terms of T1 and compression ratio and gamma. Okay, so, if you simplify this one, okay, this is a very simple this one. So, due to the shortage of time, since we have to see the numerical question also, so I am writing the final step. So, this is the final equation 1 minus 1 by, okay, let me write 1 minus 1 by. So, simplifying, you get the thermal efficiency is equal to 1 minus, okay, 1 by 1 minus this term, this is the final term, okay, 1 minus 1 by R power okay, 1 minus 1 divided by R power gamma minus 1 into 1 minus 1 by into RC power gamma minus 1, RC power gamma minus 1, RC power gamma minus 1 by gamma into, so this minus 1 will be here divided by gamma into RC minus 1, gamma into RC minus 1. So, this is the, anyway I have clearly written here, okay. So, equation 12 is the air standard efficiency or the thermal efficiency of the diesel cycle, okay. So, this you will get after simplifying this one, okay. So, here there is one bracket, okay, this will be the. So, 1 minus in the denominator 1 by R power gamma minus 1 into this term is in the numerator divided by this term in the denominator, okay. So, there will be one bracket for this, this is into, okay. So, into this term. So, now it is clear. So, if you see the compression ratio, compare the compression ratio for the petrol and the diesel engine. Normally for the petrol engine it is in the range 6 to 10 or 12, okay, approximately in the range 8 to 12, and for a diesel engine which has got a high compression ratio it is about 12 to 16 or 18, okay. So, increasing the compression ratio obviously increases the efficiency of the engine, but there is a limit beyond which the compression ratio cannot be increased, because once it exceeds a limit, then there is the knocking issues and all will happen, the auto ignition of the fuel takes place. So, there is a maximum limit up to which the compression ratio can be increased. Now, with this background, let us solve a numerical question. An air standard diesel cycle has a compression ratio of 20 and heat transferred, the compression ratio is given as 20, R is equal to 20. Heat transferred to the working fluid per cycle is 1800 kilojoule per kg. So, the properties similar to the Otto cycle are given. At the beginning of compression, the pressure is 1 bar, temperature is 15, the temperature of the air is 15 degrees centigrade. Determine the pressure, temperature and volume at each point in the cycle and the thermal efficiency of the cycle and also the mean effective pressure. Almost a similar problem, where the reason why I have selected this quite lengthier problem is we can find the pressure, temperature and volume at all state points 2, 3, 4, then heat supplied, heat rejected. The difference between heat supplied and heat rejected gives the net work done during the cycle by the engine, and when you divide the net work done by the heat supplied, we will get the efficiency, and of course efficiency can be found out using the value of gamma, RC, compression ratio, etc., and the mean effective pressure. So, let us write the given data. Though the solutions are provided, let me solve as quickly as possible. P1 is given, initial P1 is given, T1 is given 15 degrees centigrade. So, convert into Kelvin, 288 Kelvin. The amount of heat supplied is given 1800 kilojoule per. Okay. So, I think it is 1800 kilojoule per kg. Compression ratio is given as 20. Compression ratio is V1 by V2 equal to 20. Okay. So, as usual, now P1 is given, T1 is given, P1 is given, T1 is given. Okay. So, let us first find out volume 1. So, using the relation PV equal to RT, MRT. So, like previous problem, to find volume 1, because at state point 1 only the volume is not known. So, let us find that volume first. To find V1, so use this relation P1 V1 is equal to R into T1. We have assumed M to be 1 kg. So, P1 is in 1 bar. So, 1 into 10 power 5 into V1 is equal to R is 0.287 into 10 power 3 or 287. So, let me substitute, into T1 is 288 Kelvin. So, this will give volume 1. So, the volume at 1 is 0.83 kg per meter cube per kg, okay, 0.83 meter cube per kg. Now, we know the compression ratio V1 by V2. So, V1 value is known, I can find V2. Therefore, V1 by V2 is equal to 20. Using this formula, V1 is 0.83 divided by V2 is equal to 20. I can find the volume at state point 2, that is after compression. After compression, let me see what is the value. V2 is 0.04 meter cube per kg, 0.04 meter cube per kg. So, at state point 1 pressure and temperature are given, we have found volume. Now, at state point 2 we have found volume. Now, we have to find out P2 and T2. So, using the basic thermodynamic relation, process 1 to 2, process 1 to 2. T2 by T1 is equal to V1 by V2 whole power gamma minus 1. The reason why I am using this relation is we know the compression ratio V1 by V2. So, one temperature is known, so we can easily find out the other temperature. So, this is nothing but R power gamma minus 1. So, this means T2 equal to T1 into R power gamma minus 1. The same equation with relation which we used in the thermal efficiency derivation. So, using this formula we can find T2. The value of T2 is 955 Kelvin, 955.2 Kelvin. Temperature at 2. Now, the volume at 2 is also found. The only thing is pressure we have to find out. So, consider the process 2 to 3, consider the process 2 to 3, process or you can use this relation also, sorry. Okay. So, now write a similar relation T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. The relation between temperature and pressure in order to find out P2, in order to find P2. Okay. Or you can use P2 by P1 equal to V1 by V2 whole power gamma also. Okay. So, or P2 by P1 is equal to V1 by V2 whole power gamma. Okay. So, that is what I have used, P2 by P1 equal to V1 by V2 whole power gamma. Okay. So, this is R. So, using this formula you can find P2, P2 will be 66.3 bar. So, using this is P2 is equal to P1 into R power gamma. Okay. See, whenever we write the relation between temperature and volume, it will be gamma minus 1, pressure and volume will be gamma, temperature and pressure will be gamma minus 1 by gamma. So, that should be kept in the mind. So, this is equal to P2 is equal to 66, P2 is equal to 66.3 bar. Because P1 is given in the problem, R value you know, gamma value is 1.4, gamma value is 1.4, okay, standard one. So, this is pressure at state point 2. P2 will be equal to P3 because 2 to 3 is constant pressure. So, this will be equal to P3. So, we have found the pressure at 2 and 3, 2 and 3. Now, I am going to use the data which is the heat supplied QS. QS is equal to Cp into, it is not Cv, it is Cp into T3 minus T2, T3 minus T2. So, here QS is given 1800 kilojoule per kg, Cp we know 1.005. So, this is equal to 1800 into 10 power 3, I am substituting joule per kg, this is Cp is 1.005 into 10 power 3 and T3 is the highest temperature, maximum temperature minus T2, T2 we have found as 955, 955. So, using this relation I can find the maximum, the peak temperature in the cycle. Okay. So, T3 is 2746.2, 2746.2, 2746.2 Kelvin. So, that is the temperature before the beginning of the expansion stroke or power stroke. Okay. So, now at state point 3 we have found pressure and temperature, pressure and temperature. So, volume is yet to be found, okay, volume is yet to be found. Use the basic equation P3 V3 equal to R into T3, P2 V2 equal to R into T2. So, R term will get cancelled, pressure is constant. So, we will get the relation between volume and this one. So, I am writing this relation V2 by T2 equal to V3 by T3. Okay. So, process 2 to 3, let me quickly write P2 V2 equal to R into T2, P3 V3 is equal to R into T3, divide this equation by this equation, the left hand side and the right hand side, R term will get cancelled. 2 to 3 is a constant pressure process. So, P2 equal to P3. So, these two will get cancelled because P2 equal to P3, P2 equal to P3. Therefore, V2 by V3 is equal to T2 by T3. In this I know the value of V2, T2, T3. So, I can find V3. Therefore, V3 is equal to 0.12 meter cube per kg. 0.12 meter cube per kg, 12 meter cube per kg. Okay. So, now the properties are to be determined at state point number 4. Let us do it quickly. Process 3 to 4, okay. T3 by T4, process 3 to 4, T3 by T4 is equal to V4 by V3 whole power gamma minus 1. We know V4 is equal to V1 because 4 to 1 is constant volume heat rejection. So, but V4 is equal to V1. Therefore, T3 by T4 is equal to V1 by V3 whole power gamma minus 1. We have found V1, V1 is known, V3 is known, T3 we have found. So, using this formula you can find T4, you can find T4. 1265.5, 1265.5, 1265.5. So, this is the temperature at 4. Okay. Now, consider the process 4 to 1. 4 to 1 is volume is constant, heat rejection. So, I can write a similar relation like this. I can write a similar relation like this. So, P4 V4 is equal to R into T4. P1 V1 is equal to R into T1. Divide this equation by this equation. R term will get cancelled. Volume is constant. Volume is constant. V1 equal to V4. Therefore, this term will get cancelled. P4 by P1 is equal to T4 by T1. Now, this P1 is given, T1 is given, T4 we have found just now. So, using this formula, I can find the pressure at state point number 4. So, what is the pressure at state point number 4? 4.4 bar, okay, 4.4 bar. And what is the volume at 4? Volume at 4 is equal to volume at 1. If you see the diagram, volume at 4 is equal to volume at 1. Okay, see volume at 4 is equal to this point. Volume at 4 is equal to volume at 1, constant volume process. So, for this problem also, volume at 4 is equal to volume at 1. Volume at 1 we have found at I think 0.83 meter cube per kg. See, this is the volume at 1. So, that will be the same value 0.83 meter cube per kg. So, we have found pressure, volume, temperature at state point 2, 3 and 4, 2, 3 and 4. So, this is the first part of the question. Pressure, temperature, volume at each point in the cycle. Okay. Thermal efficiency and mean effective pressure. So, second part of the question is thermal efficiency. Qs minus Qr divided by Qs, that is W net divided by Qs. Okay. Qs is given, Qr we have to find out. So, Qr is equal to specific heat rejection at constant volume. So, T4 minus T1. So, substitute the value. C4 is Cv is 0.717, okay, 0.717 into 10 power 3. T4 is 1265.5, 1265.5 minus T1 is 15 degree I think 288 Kelvin. So, you will get the heat rejected, already heat supplied is given, heat rejected is 700.8, okay, 700.8 kilojoule per kg, heat supplied is given in the question, okay. So, now I have found heat rejected during the process 4 to 1. So, therefore, thermal efficiency is equal to, that is 1800 minus 700.8 divided by 1800 into 100. So, you will get the value as 61 percentage, 61.1 to be more specific. And the last term which you have to find out is mean effective pressure. So, a similar formula, mean effective pressure is the net work done during the cycle divided by the volume V1 minus V2, that is the swept volume. W net divided by V1 minus V2. W net is Qs minus Qr divided by V1 minus V2. So, this is 1800 minus 700.8, V1 is 0.83, V1 is 0.83 and V2 is 0.04. Okay. So, that will give you 1391 kilopascal, 1391.4 kilopascal. So, this is the fictitious pressure if acted on this one on the piston would produce the same amount of work that has been produced in the actual cycle. That is the mean effective pressure. Now, to summarize, in this lecture number 8, we have seen the diesel cycle, the PV diagram, the TS diagram. There is only one change in the process when we compare this with the Otto cycle. In the Otto cycle, the heat addition takes place at constant volume, that is process 2 to 3. Here the process 2 to 3 takes place at constant pressure. That is the only difference between the Otto cycle and diesel cycle. Otherwise, the process 1 to 2 is isentropic compression, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection, which remains the same. We have derived the air standard efficiency. One term that has been introduced new is the cutoff ratio, that is the volume at 3 divided by volume at 2. So, which was not there in the Otto cycle. Otherwise, the compression ratio remains, compression ratio formula is the same V1 by V2 in both Otto cycle and diesel cycle. The compression ratio for a diesel engine is higher, it is in the range from 12 to 20 or 18, it goes up to 20, whereas the compression ratio for a petrol engine is in the range 8 to 12, or it can be from 6 also, 6 to 12 also. There is a limit beyond which the compression ratio cannot be increased due to knocking issues or detonation or the auto ignition of the fuel. So, in order to prevent that, the compression ratio has to be, there should be a maximum limit beyond which it should not be increased. So, this is with this come to the end of the lecture number 8. See you in the next lecture. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.